My name is AJ Both. I'm an extension specialist in controlled environment engineering at Rutgers University. In this overview, we will try to answer the question, are LED lamps better for crop production in controlled environments? Which is a timely topic since the industry is going through a transition from high-pressure sodium lamps to the more versatile and energy-efficient light-emitting diode or LED lamps. Before we can compare different light sources, we need to review how light is measured. Different instruments are used to assess the performance of a light source, and the results can be used to make light maps, spectral graphs, or efficacy tables. Using these tools, we will review the main differences between HPS and LED lamps and conclude with some comments about which lamp type is better. In order to assess lamps used for horticultural applications, we need to review the various measurement procedures we use to evaluate lamp performance. Here's an example of light measurements collected with a quantum sensor over a 25-day period. The sensor records the light intensity at a specific time interval, for example once every minute, throughout the day and night, resulting in the distinctive peaks and valleys shown in this graph. Clear and sunny days can easily be distinguished from cloudy and overcast days. In addition to the instantaneous measurements shown in the graph, we can calculate the accumulated amount of light received over an entire day. In that case, we get a single number that represents the total sum of light received. We call this sum the daily light integral, which is often abbreviated as DLI. This graph, full of dots, shows the measured DLI values over a 22-year period for Newark, New Jersey. The horizontal axis shows the day of the year, with 1 representing January 1st and 365 representing the last day of the calendar year, or December 31st. The trend shown in this graph will be similar for other locations across the US, albeit that the DLIs will generally be lower for locations north of Newark and higher for locations further south. Note that the variation during the winter months is not as high as the variation during the summer months. By knowing the outside DLI values and the transmission losses as light travels through the glazing material, we can determine how much light is available for crop production. If that amount is insufficient for the desired crop growth and development, supplemental lighting can be used to improve the light conditions. Historic solar radiation data is available, for example, from the National Renewable Energy Laboratory, allowing researchers from Clemson University to compile so-called light maps for every month of the year across the United States. You see the results of their work in this slide, and these images can be used to assess how much light, on average, a particular location receives throughout the year. This information can then be used to determine, again on average, how much supplemental lighting is needed to grow specific crops at a particular location. The spectral output of a particular lamp will help us assess how well it aligns with the plant's particular spectral sensitivity. Researchers use spectroradiometers to make these measurements, and this slide shows how that is done using an LED lamp made of red and blue LEDs, resulting in a magenta light color. Note that these measurements are typically performed in a laboratory. Using the measurement procedure shown in the previous slide, we can compare the spectral output of different lamps to get a better understanding of how different they are. This slide shows the spectral output of different lamp types used for horticulture applications and includes the solar spectrum for reference. The horizontal axis covers the 300 to 1000 nanometer waveband in increments of 100 nanometers. The vertical scale is from 0 to 1, and the value of 1 represents the maximum intensity across the 300 to 1000 nanometer waveband. The bottom 6 graphs are for LED lamps, and they show that even within a particular lamp type, there can be important differences in spectral output. If we want to measure the efficacy of a particular lamp or fixture, we need to use an integrating sphere, as is shown in this slide. The integrating sphere is closed during the measurement, allowing it to capture all the light that is produced by the fixture. At the same time the light output is measured, the electric power consumption is recorded. Combining these two measurements allows us to calculate the efficacy in micromoles per joule of the lamp or fixture that was tested. This table shows the power consumption and light output of a selection of different lamps or fixtures that were evaluated using an integrating sphere. The corresponding efficacy numbers are reported in the last column of the table. Note that the efficacy numbers are highest for the LED fixtures tested. Lamp manufacturers are reporting even higher efficacy numbers for their most recent models than reported in this table. Efficacy values as high as 3.5 micromoles per joule have been reported in product literature. If we want to assess how a particular light fixture distributes the light across a growing area, we can use a darkroom as shown in this slide. A light sensor is moved across a predetermined measurement grid placed some distance below the lamp, and the measurements are used to make light distribution maps. These measurements can also be used to calculate the light uniformity across the growing area when an array of lamps or fixtures is mounted overhead. This slide summarizes the different measurement equipment we use to assess lamps used for crop production. Most growers will be familiar with quantum sensors that are used to measure the photosynthetically active radiation. Researchers use spectral radiometers to determine the spectral output of specific light sources. Testing laboratories use integrating spheres and darkrooms to measure the power conversion efficiency, also called the efficacy, and the light distribution of specific light sources. All of these measurements are important if we want to fully assess the suitability of a particular light source for a specific horticultural application. The most common light source used for greenhouse crop production is still the high-pressure sodium lamp. In this slide, we compare the key advantages and disadvantages of HPS versus LED lamps that greenhouse growers use for supplemental lighting. Note that this comparison does not include lamps for photoperiod lighting. LED fixtures manufactured by reputable lighting companies have higher efficacy values and have a longer expected operating life. LED fixtures can be designed with specific plant spectral needs in mind and often allow for changes in spectral output depending on crop status. The output of LED fixtures can more easily be dimmed, allowing for control based on plant needs. But the purchase price of LED fixtures is still higher compared to HPS fixtures. In the long run, this higher initial investment can be recovered by lower operating expenses. One key difference between HPS and LED lamps worth highlighting is the difference in the type of heat they produce. HPS lamps produce radiant heat that can be useful when heating is needed to maintain the desired crop temperature. However, radiant heat often creates challenges for the crop when no additional heating is needed. It can also cause non-uniform heating, since only surfaces with a direct line of sight from the source will receive the heat. LED lamps, on the other hand, produce more convective heat, often released through a heat sink or an active cooling system. And that heat can be more easily removed from the growing environment. As a result, LED lamps can typically be placed closer to the plant canopy, resulting in lower light losses. Answering the question we started with is not so easy. The choice between HPS or LED fixtures depends on a variety of factors that are listed here, and most of these factors are site-specific. Growers considering upgrading from HPS to LED fixtures may find that the benefits don't outweigh the cost, or the payback period is too long. Growers considering new installations may want to focus on LED fixtures since they are expected to be the dominant lighting technology in the near future. In any case, growers are strongly encouraged to discuss their options with a plant lighting expert. Because LED technology is relatively new and offers unique capabilities, it will take some time to develop so-called light recipes. Therefore, growers are encouraged to conduct their own experiments using a small area and evaluate desirable crop characteristics, for example, enhanced flavors. That way, any necessary adjustments can be made without creating major challenges. Growers are recommended to investigate any financial assistance programs that may be available and to keep up with the latest developments. Keep in mind that it is important to use the correct sensor to measure light levels available for crop production, and consider using a commissioning process for new lighting installations. It is my prediction that in 10 years from now, all crop lighting systems will use LED technology. The book titled Light Management in Controlled Environments is recommended as a useful reference source on plant lighting. It was written by a group of experts and scientists and covers a broad range of topics related to crop lighting systems.